All right, let's get going. So this is Introduction to Machine Learning, ECSC 840. I'm constrained by how far I can go with this cord. Welcome, everyone. As I bust the microphone off of my chest for the first class. Let's see if I can get this book back together. There we go. So, thank you, everyone, for coming. And I will start right off by talking about why we're all here, right? So machine learning has a probably huge impact on everyone's lives, both engineers and scientists, and also just like normal people like your parents, right? And so this course is basically an introduction to modern machine learning methods. And we'll talk about exactly what that means as we go. My goal is to basically kind of give you the tools, the terminology, to be able to understand what people are talking about when they talk about machine learning. And maybe also to make you a little more of a critical thinker about what machine learning and artificial intelligence really mean. This is a great class to take to prepare yourself for future classes in machine learning, of which there are many at RPI, both in the ECSC department and in the CS department. So we'll talk about that in a minute about what those classes might be. But first of all, I want to start off with going back to the very beginning in an attempt to define what is we mean by machine learning. Okay, so machine learning, if we're going to really take it back, you could say kind of started in the, well, first of all, about me. So. Sorry, about me, I am Radke. So I'm in ECSC. I've been there for about 25 years almost. I joined 2001. So I went to college at Rice. I'm from Milwaukee. I went to grad school at Princeton. And you may know me from, I do research in computer vision, but also you may know me from taking probability and seeing me in all the probability bites videos. So I recognize a couple faces from that class here. And so this is the first time teaching this machine learning course. So it's been a summer of reacquainting myself with all these ideas from the literature. And so you and I are kind of going through this together for the first time. I've got the class mostly planned out, but till the end, we'll have to figure out what's going on exactly towards the end. So this is probably one of the very early machine learning predecessors, right? So in the late 1600s, there was a lot of interest in insurance, right? And so the idea was that, places like England and the Netherlands wanted to start selling what are called annuities, which means that you pay an upfront amount and then every year you get a fixed amount until you die, right? And so the question is, how should those annuities be priced? Another issue for military matters were things like, how many, military-aged men do we have in our environment? Kind of related to stuff like census taking and so on, right? So, there really was no systematic way of gathering this data until around the 1600s when Halley, of Halley's Comet fame, started to make these so-called life tables, right? So this table kind of shows us, out of 34,000 people living in a certain city, what portion of them were a certain age, right? Now, you wouldn't call this machine learning, but you would sort of maybe call it the beginning of collecting data, right? And so maybe that's the very first thing that I would think about. Then kind of in the 1700s, 1800s, 1900s, we started to develop all this great mathematical theory of probability and statistics. And so we'll talk about, probability for sure, actuarial science, all that stuff. The real next decision point, I would say, would probably be kind of like in the 1950s, right? So in the 1950s, two things happened. One was that, we were kind of coming off the war, right? So there was a huge amount of kind of R&D effort and investment in doing things like predicting the trajectories of airplanes in the sky, or predicting the basically prediction type stuff. Where will the enemy be and how much force will they have? And in parallel, there was a revolution in computing, right? So suddenly computers kind of came on the scene, and it became possible to kind of think about computer science as a discipline. Kind of before the 50s, there really wasn't this idea of computer science as a field, even though we take it all for granted now. And that's because, universities started to get these massive room-sized computers, right? But the dream of having miniaturized computers on your desk and so on in a university setting suddenly became a possibility, right? So that was kind of like the 50s. And in the 40s was kind of like the first idea of what was called an artificial neuron, right? So this was called the perceptron. We'll talk about this in class. Basically, there was this guy, Rosenblatt, who designed this machine. So it was a kind of combination of hardware and software. And what this machine could do would be to look at a grid, like a 20 by 20 grid of pixels, like it's like a very crude small image, and be able to classify that image into one of two classes, right? Left or right, or A or B, or something like that. So here's a picture of Rosenblatt with his perceptron, right? You got a couple of big lights. This thing over here has got the camera in it, and then you're trying to classify, is this a C or is it a B or something like that, right? This seems like super crude by today's standards, but this was really the first kind of learning algorithm that was demonstrated to the public. And the thing that made the perceptron interesting and unique was that it learned from making mistakes, right? So it started with an idea about how would I divide, the classes B and C, and then when it made a mistake, a misclassification error, it would say, okay, how am I going to adjust that line? So let me actually kind of illustrate that for a second. So the idea was that if we had, a bunch of X's and O's where these were two different classes, there may be some X's over here and some O's over there. So basically, maybe the machine starts in one place and says, this is what I think the dividing line should be. And then we say, oh, actually, this guy was classified wrong. And then the perceptron says, okay, I'm going to make an update to my hypothesis about how to divide these two classes. And now I'm going to move it over here, right? And the machine says, oh, well, this thing is wrong. And then the machine moves this over here. So there was this idea of adaptation, right? And that's kind of important for what distinguishes machine learning from just like an algorithm, right? There's this kind of idea of some sort of feedback where the machine updates its abilities based on data, okay? And if you look at the New York Times article about this perceptron, the headline is, let's see, the embryo of an electronic computer that expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence, right? And then it goes on to say, all the details about this thing. So again, while you could argue that some of that kind of came to pass, I think it's also like an early example of AI hype, right? So certainly any news articles you read today about generative AI are all about kind of like, how the world has been changed, right? So that's kind of what I want to convey partially via this class, is getting you to understand what's under the hood of these algorithms. Maybe we'll demystify them a little bit, and maybe you'll not be so credulous when you read these articles about how AI is this amazing thing that's changing the world. I mean, it is cool, don't get me wrong, that's why you're taking the class, but I want us to be kind of critical about what we're seeing. So this was kind of the first example of what you would call a neural network, which I think you've probably heard that word before, and we'll talk a lot in class about what neural networks are. Now, neural networks were at first perceived as being like super cool with like tons of potential, right? And there was a lot of hand-waving about whether or not the way that we assemble these electronic components mimicked in some way the way the human brain worked. And I think that, the jury is, I wouldn't say the jury is out, but certainly I think it's fair to say that the development of these algorithms is not really that much like what the human brain does. I mean, there's been a lot of like after the fact rationalizing to say, oh, there are neurons and there are connections and so on. But the artificial neural networks that we build and the way your brain works, I think, are two substantially different things, right? And so part of the problem was that, so this perceptron came out and suddenly it was like a big deal. Everyone started to do experiments with it kind of throughout the 60s, right? And the basic model, just to kind of give us a, idea, is that we have data. That data goes through some sort of model, and then we get some sort of a predicted output. Wondering whether I should zoom in on this a little bit here. Well, let's leave this for the moment, and then I'll fool around with this in the next lecture. So this is basically guided by a bunch of examples of inputs and outputs. And this is what we would call the training data. So the idea is that you would show the algorithm a whole bunch of examples of labeled inputs and corresponding outputs, and then you'd ask it to learn that relationship, right? The important thing is to understand how to make this model generalized, right? So that when you show it something it hasn't seen before, it's learned something kind of generalizable from all the data it's seen, right? So yeah, I may ask all of you to write, capital B, collect all those things, train my algorithm to learn, and then I ask some person from outside, okay, could you write a B on a piece of paper and I'll see whether it works. In theory, the training data population of examples should be representative enough about the broader world that this should be enough for me to learn about new things. As we'll talk about as we go on, there's a danger that if I only asked one person in class to write the letter B 50 times, then I asked it to generalize someone else, there wouldn't necessarily be any expectation that we have enough kind of richness in the training data to be able to tell what's going on next, okay? And so the basic idea is to be a little more expansive. We have, the training data. We have the model. The model is kind of defined by some parameters, right? The parameters are optimized or tuned to get the best result, and then we have output, right? So for example, in that picture I showed earlier with the straight line, the location of that line was the model, right? And that's defined by two numbers, right? Slope and intercept, right? So the idea is that I keep on tuning these two numbers until I get the best performance on the training data, okay? Then you fix these parameters and you've said, okay, training is now done. Now what I'm going to do is I'm going to take some testing data that the machine has never seen before. I'm going to put it into this fixed model where this is basically fixed parameters. And then I'm going to get some outputs there. And then I'm going to evaluate how well I did. And so this kind of paradigm continues today. And we'll talk about lots of different ways of this kind of parameter optimization process and lots of different ways of talking about what is the right model for a given type of data, okay? So this general subject was called pattern recognition at the time. So basically, pattern recognition is kind of like a catch-all word. And actually, we had a course in ECSE called pattern recognition, probably, I would say, dating back to the 80s or something like that. So lest you think that computer science has the, the lock on history of machine learning, I'm willing to bet that our pattern recognition course is definitely older than CS's intro to machine learning class, right? So that's something that we've been talking about in EE for a long time. And I'll say a few words when we get to the syllabus about like my attitude versus CS attitude. There's not that big of a difference, but we'll talk about it a little bit. Now let's talk about AI for a second, right? So AI is basically, the phrase that everyone is using now. And so that kind of word kind of came into favor, again, kind of at the same time that the original perceptron enthusiasm was dying down a little bit, came a bunch of experts, including these guys here. You probably heard of Claude Shannon. He's a famous, information theory guy. But this guy, Marvin Minsky, is also like a super famous, kind of both philosopher and scientist. And so this was a proposal that they made to kind of investigate what would it take to achieve AI, right? Which, again, was never really super well defined, and it's still not well defined today. The kind of fuzzy terminology is basically like a machine that can think as well as a human can and can do tasks at the same level that a human can, right? And so when people started talking about AI in like the 50s and 60s, a lot of what they meant when they said AI was basically what I would call expert systems. Expert systems are kind of like, I'm not an expert in them, oddly enough, but they're kind of what I would consider to be kind of like big if-then trees, right? They're kind of like complicated sets of rules that make good predictions, right? So there's not necessarily the same notion of learning and probability. It's more like you want to derive a, kind of a rule-based model for the world, right? And that became more successful for a time because it turned out that it was very hard to train these neural networks at some sort of scale, right? Yes, you could do this like 20 by 20 pixel experiment, but for a real world experiment, you'd need to have lots and lots of perceptrons hooked together, learning on data that was much larger. And at the time, it just wasn't computationally tractable. And so when people started talking about AI, it was more about how can we design these good rule-based systems, right? So for example, a really naive way of, so a standard machine learning problem is called classification, right? So a kind of rule-based system for kind of spam versus legit email might look at the distribution of words in the email and also, things like spellings and so on, right? So for example, it might know that if I'm trying to make the decision between, classification algorithm, spam or, I saw it called in one lecture ham. I've never heard anyone call real email ham. I'm going to call it legit email, right? So, I may look at some features of the email, which could include, like, for example, a list of words that are in the email or a histogram or something like that. And I might, say that if the word, Viagra appears in the email, that's very likely to be spam, right? But that's a rule that I design as a human, right? So then, there's this kind of this arms race between, spammers and rules that say, okay, well, maybe I stop getting emails that say Viagra and I start getting emails that say this, right? Trying to get around these rules, and then someone has to go and then implement this new rule, right? So the better thing would be to have some sort of adaptive algorithm that does that, and that's what we're going to kind of mostly be talking about here. Another kind of AI what I would call hallmark was stuff like solving search problems efficiently, solving mazes and things like that. So like, I know that there's an intro to AI class in the CS department, right? And I looked at what they talk about in that class, and some of the first stuff they talk about is like search algorithms, and that's not something we're going to talk about in this class at all. Like, I don't consider that to be machine learning, but in the early days, that was kind of considered to be part of AI, right? Okay, so then we move on a little bit. One thing that really changed, well, let me just also say, this is something that I really have a little bit of a problem with, is I really don't like the word AI or the phrase AI because I think that it doesn't really mean anything, and also I worry about the way that people use it to affect policy and so on, right? So, for example, if any of you have read any books by this guy, Ted Chiang, he's a famous science fiction author. He wrote the book that Arrival, the movie, was based on. Great author. So, someone asked him, what is AI? And he said, someone said it was a poor choice of words in 1954, right? A better choice of words might be applied statistics or something like that, right? And even now, I was at a meeting 2 days ago where someone said a couple things I was like, blew my head off. I was like, one was, we're living in the age of AI. And the other one was, we have to interject more AI into our curriculum. I was like, well, what does that really mean, right? We've got tons of machine learning courses. What do you mean that we don't already have, right? And no one could really say what they meant other than that we needed to do more of AI, right? So this is not what I would call an AI course. When I say machine learning, I feel like I'm on firm ground. I know what it means. I can define it for you. We can talk about different types of machine learning. When I say AI, I feel like it's just a buzzword that people are using, right? Okay, so one thing that really moved the field along was the development of what are called benchmarks, right? So benchmarks are basically big data sets that then kind of form a competition in some sense, where you say, okay, I'm going to try to get my algorithm to do the best job of classifying these small black and white images into the 10 digits, right? So in the 80s, it became possible to kind of not only develop such benchmarks, but also to distribute them. And that's something that you maybe don't think about too much. We'll talk about that a little bit more next week. Email and the internet didn't exist in the 1980s, right? So what you had were FTP and punch cards and dial-up modems and so on, right? So it wasn't so easy to have a web-based leaderboard on a certain algorithm or a certain data set that showed you how well you were doing. That only kind of came to pass as we moved into the 80s and 90s when personal computing and so on and the World Wide Web became a thing. So in a way, all these non-machine learning technologies did advance machine learning in a way, because otherwise these competitions wouldn't have been possible. So we'll talk a little bit about data sets. That's going to be something I want to talk about a lot in the next lecture, okay? So then, like pattern recognition, machine learning, statistics, all this stuff kind of like continued to roll along until I would say maybe like the mid, 2010s, right? And if any of you know anything about the history of neural networks, you may know the story about how like Jan LeCun, for example, like the meta, father of neural networks, was kind of on the outs research-wise, or not on the outs, but certainly he was not like the dominant machine learning researcher in like the 1990s, right? Because neural nets were seen as like not cool, hard to train, like didn't have great performance, and other methods were better, right? And then suddenly, around 2010 was when there was like a switch that was flipped. And one of the things that was critical was this benchmark data set that was released called ImageNet. We're going to talk about that a lot more on Tuesday. Basically, ImageNet was an attempt to have basically a bunch of example images for every kind of noun in the English language, more or less. So there was this taxonomy of words, and then the idea was for every word you'd have a bunch of examples, and then you'd annotate the examples. So here we have pictures of snakes, for example, right? So this is a snapshot of ImageNet as it was released in 2009, and at that point it already had basically 5,000 categories and 3 million images, which was well beyond the size of any machine learning data set that had been out there before. And this was like a real challenge to the computer vision community of how well can you do on this data set. And then there was a very famous neural network algorithm called AlexNet that had amazing performance on this challenge, right? Like, usually when you're looking at a benchmark and you see improvements, they're like, 0.5% over the state of the art. AlexNet was like way above anything else on ImageNet, and that was like a deep learning prototype neural network algorithm. People were like, well, wait, maybe neural networks are actually good for something after all. And suddenly the switch flipped, and then everyone was doing neural networks of different kinds to solve these kinds of problems, right? And so what caused that switch to flip? So one was the availability of very large data sets like ImageNet. One was basically the availability of commercially available general purpose graphics cards, right? So, Curtis Priam, RPI alumnus, you can thank him for some of this stuff, right? So GPUs that you could buy and put in your computer, suddenly universities were able to buy graphics cards and run deep learning algorithms on them in ways that were just not possible like, a few years earlier. And then again, these competitions where everyone could see how well things were doing and understand what it was that they had to beat really accelerated the state of the art. And of course, now we're in the 2020s, and it's maybe not quite fair, but I would say that when someone says AI, what they really are probably talking about is kind of like deep neural network based something or other, right? And so that's kind of where we're at right now. So we will talk about neural networks in this class, obviously, but it's not going to be the only thing we talk about, right? So if I draw kind of like a little picture, kind of what I would say is that, we have a big blob, which I would call AI, right? And then we have a big blob called, machine learning. There's a bunch of stuff that is AI that's not machine learning, right? And then we have a bunch of stuff that is basically like neural network based machine learning. And then we have, kind of like deep neural network stuff. And then within that, I would say you have like generative AI, stuff, right? So what we're going to do in this class is basically, inside this ML bubble. I know probably a lot of you are super interested in what's inside this thing, right? But to understand this, you have to understand what's inside the bigger picture, right? So that's what this course is about. And so I just taught a class last year, and I'm going to hopefully teach it again in the spring on generative AI, right? So if you take this class, you'll be all set to go to learn about generative AI in spring 2025, right? But I think that still, my understanding certainly of the field is that whenever you go for like a Google job interview, they're still going to ask you about lots of stuff in this bubble here, right? Stuff that is like kind of not necessarily the deepest neural network stuff. They'll ask you about, support vector machines and kernel methods and stuff like that. We'll talk about that stuff in this class. I want to make sure that you're well prepared for that type of job interviews. At least you've heard these words enough to know what they mean and can go back and look it up again later, right? Okay, so let's talk a little bit about what I want to do in this class, right? So kind of examples of, or types of machine learning problems. They're kind of, I would say, whoa, what's up with this? Hey, go home projector, you're drunk. Let's focus, get in the game. Clearly there's no machine learning going on in this thing, or if it is, it's pretty weak. See if I can get it to focus. Normally, all right, let's do some sort of, all right, freeze the focus. All right, so a big one is what's called supervised learning. So supervised learning is basically kind of the drawing I did before, right? We basically have like data, comma, outcome pairs, and we have these labels, right? So, I give you a bunch of pictures, and I call these are all cat pictures, and these are all dog pictures. Now I want to design an algorithm that separates the cats and the dogs, right? So there are kind of two main subclasses of this problem, right? So one subclass is called classification. And classification is basically like, cat versus dog, right? So, in that case, it's called a binary classification problem. Like I could have, binary classification, where it's either like, cat or dog, or yes or no. Or I could have multi-class classification, where, for example, I'm classifying, those digits that I showed you earlier into the set of 10 possible categories. But the point is that I'm making a hard decision into one of the classes, and there's no like gray area in between the classes. It's any one of those classes, right? So we're going to talk a lot about these kinds of problems. And then there's something called regression. So regression is basically where we still have kind of data and output pairs, but instead of the outcome being a, I'm in probability where I should call output, not outcome. Instead of the output being one of a set of classes, the output is a real number, right? So in regression, the output is a real number, right? So I could be, for example, predicting a stock price, and that stock price is, $987.15. Or I could be predicting a location, like a GPS location. So I have basically like, kind of like a vector of, x comma y. And so the problems of regression and classification are a little bit different. One, I'm predicting kind of like 1 of n, and the other one I'm predicting a number that could be anything, right? And then there's what's called unsupervised learning, right? So supervised learning is one thing. Unsupervised learning is basically something where I don't have any output labels. All I have is basically data. And I put this into some sort of box. And then we'll kind of talk about what comes out is some sort of like, structure, I would say, for example. So, for example, what I might do is try to think of an off-the-shelf, like unsupervised learning problem, right? So here's an example. It's a little bit complicated problem, but if you're a biologist, you might have a situation like this. So here is a super complicated, matrix that came from doing an experiment. So maybe you've heard of microarrays. Microarrays are basically like little wells where they have, kind of a matrix of lots of different cancers, more or less, or diseases or whatever. And then on the other axis, they have lots of genes. And they kind of want to see what is the magnitude of gene expression for each of these cancers, right? And so basically, you have this big matrix where maybe green means high, expression, and red means low expression. And then there's no labels, right? You just kind of want to learn something about this data, right? So one thing you might want to learn is, okay, so for gene number 12, what, cancers does it kind of cluster with, right? Or kind of conversely, for a given cancer, what genes is it most associated with? And kind of what combinations of genes and cancers kind of go together, right? So you're trying to learn something about the data, but you don't necessarily have any sort of labels about, any preconceived notions of what structure there is in the data. You're trying to pull something out of the data, okay? And so unsupervised learning, is something where, again, I have like, hundreds of, so to take another example, imagine that I have collected all of you writing the letter B on a piece of paper. That piece of paper that you give me may be, maybe I digitize it into like 100 by 100 grayscale image, right? And then I want to find out, okay, well, what is the structure of all the B's that people are writing? Is it really like 10,000 dimensional? Like, are there really 10,000 degrees of freedom? Could those pixels be anything? No, of course not. Those pixels are they're only probably a few dozen or even less dimensions of how this kind of shape of the B can change. And unsupervised learning can kind of help us reveal how to do what's called reducing the dimensionality of this image into just a couple of knobs that by turning these knobs, I can generate all the image examples that I saw, right? So again, there's no output there. It's just trying to understanding kind of hidden structure of the data. And then a third type of learning that we will talk a little bit about, but not a ton about, is called reinforcement learning. And so reinforcement learning is basically something where there's a little bit more of a feedback loop in the sense that, you know, you've got an agent, like a robot, for example, that is taking some sort of action, seeing what happens in the world, and then modifying its plan to do something else the next time, right? So the classic example of a reinforcement learning problem is like what's called a bandit, right? Or even like, well, so let's suppose, you know, I've got like, you know, only a few dozen summer, this is really morbid, like say I've got 40 years left to live, right? There's a limited number of vacations I can take. So I can say, okay, well, I've gone on a bunch of vacations and there are places that I would really like to go back to. I know that I would have a kind of guaranteed reward of going back to that place, or I could try to go somewhere new and hope that I enjoy that place even better than the places I've been already, right? So there's kind of like this idea of I explore the space by going on vacations, and I exploit by going to places I liked a lot, but I don't want to just like miss out on things that may be happening. So the idea is I'm taking actions, I'm seeing what I liked, and I'm deciding what to do next, right? So basically the idea is, you know, learn some sort of optimal actions based on outcomes of past actions. You know, a good example of this is also like, you know, the AlphaGo algorithm that learned how to play Go and beat all the Go masters, right, was a reinforcement learning based algorithm where it basically started out by kind of like making random moves, and then it slowly got better by seeing how well those, you know, how well those moves and strategies worked, until by the end it was performing better than any human was, right? So there was no necessarily explicit, well, I shouldn't say too much. Let me just say that that's an example of reinforcement learning where I play a bunch of games, and as I play games, I get better and better until I'm doing the optimal thing, okay? And so I would say, just like to characterize my guess about how this class is going to go, I would say it's probably going to be like mostly supervised learning, you know, some unsupervised learning, and then maybe a little bit of reinforcement learning type stuff at the end, right? There's a whole class this semester taught on reinforcement learning, right? So, you know, if you want to learn more about reinforcement learning, you'll be in a great position after taking this class to go and take that class, right? Okay, so actually, you know, this is kind of a good point maybe to look at the syllabus, or maybe actually, let's just, for example, since we're talking about classes, let's take a look at Quacks. So if I look at what's being offered, you know, in our department and in CS these days, right? So, you know, above the 4,000 level, at the 6,000, so this, you know, probabilistic graphical models, right, is basically, you know, kind of a specific kind of machine learning. We'll talk a little about this, maybe like one lecture on this in class, as whetting your appetite to take this class, or the, you know, this further class. I feel like my class should be numbered lower than this, but all right. Then you've got stuff like decision making under uncertainty, reinforcement learning, AI for networking. You know, there's a course on what is it called? Dr. Yell. Oh, this is her course. This decision making under uncertainty. So, you know, you'll be well posed to take any of those kind of classes after you graduate from here, and then over. No, not Earth. We don't care about the Earth. Computer science, you know, has reinforcement learning. I know they have more than this at the 6,000 level. AI for conservation, I'm not sure what's going on there. AI for science, sense making, I don't think that's an AI course. Logic-based AI. So there's a whole bunch of classes, deep learning on graphs, machine learning from data. So yes, so all this stuff I think you're going to be well posed to take. Now one question that I think is a natural one is like, there is a CS class on intro to machine learning, right? Or they call it machine learning from data. And so what's the difference between that class and this class? I would say there's a sizable overlap. I haven't taken that class, and I haven't taught this class yet, so it's kind of hard for me to say exactly what the difference is. I wouldn't say that you need to take both, put it that way. You'll learn a lot of the same stuff in each, and I don't want to speak for what Malik does in his class. That's a super duper popular class, right? I think that this class will be, first of all, it'll be more intimate, I think, because it's a smaller class. Second of all, I feel like I have a little bit, maybe more inclination towards, well, again, I can't really say not knowing what Alex's class is actually like, but my personal philosophy is to give you, understanding about terminology, try to instill some intuition about why things work and how they work, get your hands dirty with actually doing experiments with real data in the homeworks, and kind of more generally just give you a broad exposure to everything you might want to know. I think that the CS course, from what I can tell, is maybe a little bit more theory-based, like a little bit more theoretical, a little bit less hands-on, but I don't really know. I don't want to say that without firm evidence. But I know that I'm definitely more of a, I mean, we're going to do a lot of math in this class, don't get me wrong, but I do feel like I also want to talk about the practical elements of machine learning as it is used today and what it's used for. I want to do a whole bunch of examples of showing you the results of different machine learning algorithms on data sets and so on. So we'll see. The short answer is I'm not really sure what the difference is. You can't go wrong with either class, but you're all here, and I hope you stay here. So, okay, so let's talk about the syllabus a little bit. So you should already have access to Piazza. So Piazza, I added everyone who was enrolled as of yesterday into Piazza. And if you haven't gotten into Piazza yet, just come up or send me an email, probably better, and I will add you to the course, right? So there's not much here right now except for the syllabus, right? So the syllabus is here. Let's scroll back here. All right, let's zoom in here. So let's go over the nuts and bolts a little bit. I guess the first thing I should say is I see everyone sweating. I'm sweating too. I have no control over the temperature in this room. I came in this summer, I was like, man, this room is so hot. So I guess the answer is to wear shorts when you come to this class, and we'll all suffer through it together, and maybe it'll be better in the winter. Although hopefully there won't be like the big clanking pipes that I hear sometimes happen in Sage. So we just have to sweat through it together. So 2 days a week here in this room. Websites. Okay, so I'm not a fan of the LMS that RPI provides, so we don't use LMS at all in this class. You already talked about Piazza. Piazza is where I'm going to post everything, where I'm going to answer questions, as a Q&A board, stuff like that. Please, post anything that you have a question about on Piazza, and ideally post it as a public question so that if it's something that people would benefit from knowing the answer to, that everyone sees it, right? The usual kind of caveats apply. Please don't post answers and say, is this correct? Those are not great things to put on Piazza, but just in general, how do I approach these problems or anything related to the class? And kind of conversely, Piazza is going to be the first place I'm going to put anything that you need to know about on. You're responsible for anything that you see on Piazza. I will also use Gradescope. So Gradescope, I think probably most people are also familiar with. Gradescope is going to be the easiest way for us to put all the homeworks and exams in one place so you can see how you're doing in the class at a glance. I also am looking into Submiti, right? So who here has used Submiti before? All right, you notice I didn't raise my hand, right? So Submiti would be a learning experience for me. I do want to give you some code assignments with the usual kind of public and private tests to make sure that you know how to write some machine learning code, right? So my intention is to have each homework be a kind of a combination of a thing that you submit on Gradescope and some code that you submit on Submiti to make sure it works. To make that happen, we have 2 TAs here. So could you guys stand up? So the TAs are Joshu up here in front and Huzaifa over there in the back. So they will be your points of contact for certainly anything that is kind of how do I get Submiti to work, programming related type stuff, right? As well as the general theory of machine learning, right? So they will have office hours. You guys can sit down anyway. So basically, the way I plan to have this set up is more or less that homeworks are going to be due, I think generally on Wednesday nights, and then I'll have office hours on Tuesday afternoons, and these guys will have office hours on Monday and Wednesday afternoons, so you should have a 3 solid days of potentially getting help on the homeworks. Let's go back to this. So the other thing I was going to say is, I am recording the lectures, or attempting to, and so I will put these lectures on Media's site to start with, which is kind of behind the RPI, Duo Push paywall. I may put them also on YouTube, depending on whether I like what I'm doing, and so for sure I'll put them on the local RPI video so you can look back at these lectures. Again, you should have access to all this stuff already, unless you add the course like this morning. So just send me an email if you haven't gotten access to any of these sites. I don't know about Submiti particularly because I'm not sure whether they auto-load students in, and when they do that, I'll have to take a look at that later today. So don't worry if you're not sure about the Submiti part yet, because I haven't even assigned the first homework yet. Okay, prerequisites. So I'll talk about this a little bit. Maybe I'll go through the syllabus and then talk about this a little bit more. What do you need to know to be able to do machine learning, right? So for sure you need to know basically multivariate calculus, right? More than just one dimension. And linear algebra is also important. Now, I know that linear algebra, some people may have an explicit linear algebra course, which is great. And I encourage you to take a real linear algebra course. What you have for matrix algebra may be good enough as long as you can generalize to matrices of higher dimensions. The other one is probability, right? So anyone who is an E or CSE major has taken or should take probability, right? So that shouldn't be a problem. I will say, though, that I get a lot of people asking me, is MAU good enough, right? Modeling, analysis, uncertainty is kind of like what non-ECSE majors take. And my answer is usually not, maybe not, I guess I would say. So put it this way. If you are an EE or a CSE major, you should have probability. I'm not going to assign anyone to the class who just has taken MAU. If you are like a biomedical engineering student or a material scientist who wouldn't necessarily take our probability class and you have taken MAU, I may let you in with the understanding that there may be some probability concepts that you would not have seen in MAU, right? So my understanding of MAU is it's a little bit more about statistics and data and tables, but not so strong on the theory of probability that's really important to understand what's going on in machine learning. So I do really think that having a probability background is important to understand what's going to come next. If you're kind of not sure about whether you're at the right level, what I would say is that, not next week, but the following week will be some mathematical lectures that will kind of give you some sense of, do I understand what he's talking about, or is this like totally foreign to me, right? If those two lectures before the drop deadline seem okay, then I think you'll be okay. If not, then we should have a conversation. Okay, so this is me, this is them. Okay, so this is a list of the stuff we're talking about, and I'll show you a calendar in just a second that is a little bit more specific. Textbooks. So I noticed, I was just at the bookstore for lunch. Well, not at the bookstore for lunch, but I was near the bookstore and I stopped by. So I did put a textbook on order at the bookstore, which doesn't seem to have arrived yet. It's this textbook, Bishop, Pattern Recognition and Machine Learning. This is a classic textbook. The nice thing about it is that I can, confident, or with a good conscience, tell you that these textbooks are available for free, right? So this Bishop textbook, for example, is free online, the exact same version as what you're going to find in the bookstore. The physical copy of this book is like super heavy. They must have printed it on like some extra thick paper, like it's like a brick. So I have it in my office, and I think it's a good book to have. That's why I'm using it kind of as the primary text. If you don't want to buy it, then just use the PDF, right? But I do want you to look at it. We're not going to assign problems out of it, but this is a good kind of general resource. And if you look at the syllabus, you'll see that I'm kind of tying lectures to roughly sections of this textbook for you to follow along. Now, there are a bunch of other books that I think are worth looking at, and I don't necessarily like everything that Bishop does. So, you'll see that in the syllabus, I listed a few other supplementary texts, which are, I think, good to have as PDFs, right? There's especially the second one called Patterns, Predictions, and Actions. That's the one that recently came out, and I kind of like that book just because I feel like it has a more kind of readable, what's the right word? It kind of looks at machine learning from a big picture and kind of talks about, I like its discussion of the history of machine learning, about data sets, about categorization. At the math level, I think it's a little bit too advanced to use as a textbook for an undergrad class, but I like the rest of it. So again, no downside to downloading this stuff. Also, there's these famous Stanford course notes, which I think that when Dr. Chen taught this course, I think he was teaching a lot from those notes. These Stanford computer science notes, feel free to download those and look at those too. The great thing about machine learning is that, even though it's a, young-ish field, there are tons of resources to get, used to understanding it, right? Another book that I like a lot, even though it's a little bit older, is called Pattern Recognition or Pattern Classification by Duda and Hart. So I may use some stuff out of that. The only thing that I think you really need to have is this Bishop PDF. But again, even that I don't think is necessarily something that you're going to be referring to all the time. But I really do appreciate having a single unified reference that uses the same notation, all that stuff, as opposed to just, kind of like winging it based on my course notes, right? Yeah, Joshua, you can take off too if you want. Yeah. Okay, so let's see. Like I said, we kind of talked about the main categories of stuff, right? Classification, regression, unsupervised learning, algorithms for density estimation. The last one is something that I'm going to try to focus on a little bit, which is kind of like a little bit more of the ethical side and the application of machine learning, right? So if we go to the syllabus, for example, just to kind of flash forward for a second. So here is a rough calendar. I think we're probably pretty solid on this calendar up until kind of like Halloween. The stuff below Halloween I'm still working on, but roughly the content is there. So Today is the introduction syllabus. Monday is Labor Day, no class, but Tuesday is a Monday schedule. So we'll meet again in this class on Tuesday. And on that class, I want to mostly talk about a little bit more of the development of data sets in machine learning as they have come to be used, and talk about some of the ethical dimensions of how people are using these data sets, right? And how machine learning is applied more generally. So instead of kind of like shunting that concept off to like the last lecture before Christmas, I want to kind of put that front and center because I feel like it's important for us to talk about. And then kind of similarly, the next lecture I want to have on Thursday of next week is going to be something where I'm going to turn it back to you guys a little bit. I'll have a set of discussion questions that I'm going to put on Piazza we can talk about. But I want to talk a little bit about kind of like, from roughly day 0 of this class, what you think about different aspects of machine learning, right? How it affects society and business and ethics and art and all that stuff, right? Just to get some reading for me about where you guys are at. So next week is kind of like a little bit more of a soft skills kind of class, talking about ethics and data sets on Tuesday, and then having a class discussion on Thursday. And if we have time, I kind of was thinking that we could come back to another class discussion, like maybe towards the end of class, to see, now that you've gotten these algorithms under your belt, is it more or less mystifying, or do you have your opinions changed based on what you learned in this class? But then as of the 9th of September, we start to get into all the actual math, right? So then from kind of then on, we start to get going. The first homework is basically going to be based on lectures 4 and 5, the 12th and 16th of September, and it'll be due later on that week. So so next week is still a little bit, easy and discussion-y, and then we'll get into the math after that. Okay, so how will this class be graded? Well, I'll tell you. So my goal is to have homeworks that are a mix of kind of paper and pencil and showing me that you've got the code working on Submiti, that we can kind of, agnostically test to make sure your code works. I'm thinking probably 5 or 6 of such homeworks, and those will be 30% total. I am not a computer scientist, so I don't hold with all this like late days, 50% stuff, either you submit or you don't, right? I'm not gonna have any late day kind of shenanigans on Submiti. The plan is also to have 2 in-class exams. So those are going to be worth 20% each later in the semester. And then a final project, right? So the final project is something that basically, well, let me talk about the other stuff before I talk about the final. So basically, homeworks, the TAs will grade. The GradeScope platform allows you to easily appeal grades, although don't abuse that privilege, right? So GradeScope is the place to submit the homeworks, and that's where you'll be able to submit grade appeals. Exams will be in here. We'll again grade them in GradeScope, and I will help out on grading those exams because I kind of like to get a reading on where everyone is. The project, though, is something that I'm still kind of like putting together, but my thinking is that the project should involve collecting your own data and applying machine learning tools to it, right? So I'll talk a little about that in a minute, but I think that what I want to talk about kind of starting on Tuesday is where does all this data come from, right? Like, it's just so tempting to think about data as something that you just kind of like right click and download without any thought of like, who created this data? Was it ethical to collect that data? Are the labels unbiased and fair? I think that in the project, by collecting your own data, you will have a sense of ownership, like everything that got into that data set. You know how you collected it, you can defend why you collected it, you can make sure you didn't have any problems collecting it. So it's kind of like one of my thinking is that that's part of the project, is to collect the data and then to say, okay, for example, I want to then have you show me that you can find some sort of like a classification problem in this data. You can find some sort of a regression problem in this data. You can find some sort of a unsupervised learning, right? So to give you a couple examples, right? So, I have a zillion colored funky shirts, right? So I could take pictures of every shirt in my closet, and then I could say, okay, I'm going to try to, correlate the picture of the shirt with how much I paid for it, right? That's a regression problem, right? Because I'm predicting the cost of that shirt. Or I could say I'm going to try to classify these shirts automatically into, would I wear them to an academic conference, or would I wear them to the classroom, or would I wear them while I'm mowing the lawn, right? So I have like home shirts, work shirts, and fancy shirts, right? That's a 3-way classification problem. Or I could basically try to just take all these pictures and cluster them together to find out what kinds of classes of shirts I have. Maybe I have an automatically discovered set of stripy shirts and an automatically solid color shirts or t-shirts or whatever, right? But it doesn't have to be images. You could say, okay, I'm going to take all the music in my Spotify library, and I'm going to For example, a regression problem would be, I want to predict the BPM, the beats per minute of each of these songs, right? So there's a real number that I'm predicting from the audio signal. Classification would be like music genre. I'm going to try to tell whether this is jazz or blues or rock or whatever, right? And then an unsupervised problem could be like saying, I want to make a playlist of similar songs to this, track that the user provides, right? What is kind of similar in the feature space? Doesn't have to be music either. It could be like if you're wearing a Fitbit, you could try to extract data from your Fitbit all semester and say, okay, can I kind of correlate the number of steps I walked with the heart rate that my Fitbit has measured? That's kind of like a regression problem. Or you want to say, can I look at the Fitbit data and tell whether this is a weekday or a weekend, right? That's a classification problem, right? So I think you can kind of have fun with it, right? The point is that I want you to be intentional about figuring out what data set to use and then find some problems that demonstrate to me that you've learned something about machine learning on that data. That's my idea. Question?
For collecting the data, can it be from anywhere? Like, can it be like from Kaggle, or does it have to be from a unique location?
I don't want it to be from Kaggle. Right? The whole point is not to have it from Kaggle, right? Because I don't want you just like right-click save as data set, here's my data set, right? I want you to have some ownership, right? So that's the part that may take you more time than you think, is collecting data, right? So for example, I also do this in my generative AI class, right? The first thing I did in generative AI was to say, okay, go out and collect a bunch of images of something, right? So like one group took pictures of like hundreds of leaves on the RPI campus, and one group took pictures of Legos, and one group took pictures of climbing holds at a rock climbing gym, right? The point was that everyone was kind of invested in the data that they created themselves, right? One group took pictures of all the characters that you could create in Baldur's Gate 3, right? And then tried to make generative AI versions of those, right? But I think that data collection process, to me, it's really important, right? So I don't want you to use Kaggle. But when the time comes, I will release very detailed specifications. And in fact, the first problem on the homework, which I haven't released yet, but it's going to look something like this. Let me pull it up here. I have not yet released it, but my thinking is that you, as a individual, kind of think about what that data might look like. I'm not going to hold you to it, but I'm going to ask you to think about it, right? So this is kind of like roughly the first homework, and let me just kind of come down to the problem I'm talking about. So this actually says literally what I don't want is a Kaggle data set, right? So this is like the third problem on homework 1, hasn't been released yet, but this is kind of like I want you to start thinking about it. You don't have to collect anything yet, but you should think about it. Now, when it comes to the actual project itself, my vision is this is a large class that I will let you do the project by yourself or with a group of 2, right? Can't do the homeworks in groups, but I'll let you do the project with another person if you want, right? And then in that case, you have to agree on what data you're going to collect, but it also may make it easier because you can split the effort of collecting the data, right? So both of you will receive the same grade if you pair up with another person. And then I'll ask you for some progress report in the middle of the semester to kind of make sure you're staying on track. One thing that you should know, in case you didn't know, is that the drop deadline policy has changed this semester for RPI. You all got it in morning mail, and then you all deleted morning mail. But basically what happens now is the add deadline and the drop deadline are the same, September 13th. What that means is that you can still drop the class after September 13th up until the November 3rd or whatever the usual 10-weekend deadline is, but it will remain on your transcript with a W next to it, showing that you withdrew from the class, okay? I didn't make this rule, but that's the way it works now. So at least this semester, you should be aware that, if I'm being honest, you're not going to really have any graded work before the dropped without a W deadline. So you're going to have to kind of get a sense of, from the first 5 lectures, is this a class that you're willing to stick with, right? Because after that point, you can still drop it, and it won't affect your GPA if you drop it after September 13th, but you will have it still on your transcript with a W, and that's all I can say about that. Okay, so course calendar we talked about. Other course policies, the usual things, right? So if you require extra time on an exam, please let me know that as soon as possible, because I need to arrange for probably a different room for you to take the exam for extra time. So I don't want to have to deal with that like the day of the exam. So any issues like that, please submit that to me early on. Generally, come to me if you have any sort of class-based issues well before we have any sort of problem. And then the usual, this is like the boilerplate stuff. I expect you to write your own code. So one thing that I want to make it clear is that Yes, there are a zillion machine learning libraries out there, right? But what I'm going to teach you, for the most part, is not something that requires you to use PyTorch and TensorFlow and use these packages, right? Everything that I'm teaching you, you should be able to write basically on your own, right? In a short amount of code. I'm not talking about like thousands of lines of code. This is not data structures, right? So I'm trying to get you to actually do it by hand, and so the goal is not for you to do it in one line with an output from a library. The goal is for you to actually try to make it work on your own. So when we start to assign homeworks, I will be a little more specific about what you can and cannot use when you submit your stuff on Submiti. And of course, it goes without saying that I don't want you to use generative AI tools to do the homeworks, right? That's defeating the whole purpose of learning this in the first place, right? So please be a good citizen. Okay, so any questions or comments about the syllabus or about the mechanics of the class? Yes?
Do you have any, like, say that we have, like, some excused absence for a long period of time or whatever reason, can we, come to you about, like, getting extensions on?
Yeah, for the most part. Yeah, that's the kind of thing to come to me about. Of course, it should be something legitimate, but if you're going to a conference or if your sports team is going somewhere, we know how to work around that kind of thing. If you're going to be gone for one of the exams, then we should definitely make sure we know about that well in advance so we don't, so we have a game plan, basically, right? Other questions? My office is up on the 7th floor of the JC in the corner, so I'm easy to find. I'll start holding office hours starting next week, although since Tuesday is a Monday schedule, that would kind of mean that my Tuesday office hours will be right after this class, so I'll go from class to my office and I'll be there. And then the TAs probably will not start holding their office hours until we release the homework, which will probably be the following week. So I'm guessing that there's no reason for the TA to hold office hours on Monday or Wednesday for what we're talking about up to that point. All right, so let's see. What else do I want to say here? Well, I mean, I guess, again, to give you some sense of, you maybe already have a sense of it. So my, lecturing style is exactly this, right? Some combination of, some slides with pictures on it, PDFs. I do a lot of hand sketching, so my notes are going to be like this. I'm going to be drawing stuff out by hand. Part of the reason I do that is because there's so much notation and equations and so on in machine learning that would be extremely easy for a professor to just like flip through a bunch of slides that have like super complicated equations on them and expect you to absorb them, right? For me, writing things down is kind of like a rate limiting mechanism so that you can see I'm doing it at the same pace. You're hopefully able to take notes. If you can't take notes that fast, that's okay. I'm going to take all the stuff that I put on pieces of paper and scan it in and put it on Piazza. So everything I write down, you'll have access to. You'll have access to the recordings. I don't have any other like PDF LaTeX up lecture notes for this class, right? So that's a little bit of a difference. I think that, it's very common when you're teaching machine learning, just flip through a bunch of slides with a zillion equations on it. I'm not that kind of professor. So that's another difference between me and other people if you're worried about which class to take. Okay, so questions, comments? Well, let me just run a couple things past you. I'm not doing any serious actual machine learning today, but just in terms of like, what kind of math and probability and linear algebra am I really talking about? So let me just write down a couple of things and see, if you understand what I'm talking about, or what the problem statement means, then that's the right level, right? If you're looking at this thinking, what is he even talking about? Then you may want to kind of rethink things a little bit. So, for example, we're going to do a lot of stuff along the lines of calculus with multiple variables, right? So if I asked you to take the derivative of this expression with respect to x, right? You should remember the chain rule, right? So like I have the derivative, this is the 1 over the thing over here. And then I take the derivative of the inside with respect to x is this, right? Something like that, right? So you should be, and I'm being a little sloppy here because this is not really that important, right? But the point is that, taking the derivatives of things is important. To kind of bump it up to, multiple variables, right? You should also understand what it means if I were to say, if this was a function, what does the gradient of that, function look like, right? That the gradient looks like a vector that is basically like the partial derivative of f with respect to x and the partial derivative of f with respect to y. And you should be familiar with, like, if I want to find the minimum of some function, right? What I should do is take the derivative or take the gradient and set it equals 0 and solve for it, right? So if I want to minimize this function, what I should be doing should be to take the gradient of the function and set equal to 0, right? If there's only one variable, then it's just the derivative, right? But if there's multiple variables, I have to have that vector and set equal to 0, right? So optimization is going to be something we talk about a lot. How do I find the best parameters? Really, that comes down to minimizing some sort of cost function, right? And so you have to be able to understand the mechanics of how that works. If you remember, hopefully from like multivariate calculus, there was also something called Lagrange multipliers, which was probably something you spent at least a lecture on, right? So, with, constraints, if I'm doing a minimization problem, then I need to have what's called Lagrange multipliers, which we're not doing right now, but that's something that I may mention, and you should kind of remember, oh yeah, I remember what that means. You have this extra lambda, and you take the constraint, you put it into the objective function. So we'll talk about that, but again, that's the kind of level of stuff I'm talking about from calculus. From linear algebra, you should be able to think about like, if I have a system like this, AX equals B, right? So, in multivar, probably you dealt with like 2x2 and 3x3 matrices. I expect you to be able to deal with bigger matrices than that in this class. In general, it's kind of like saying I have a square matrix and I have a vector, and I want to, find the values of x that satisfies the equation simultaneously. Right? So systems of simultaneous equations, in MATLAB, I can just say b equals a backslash x, right? Or you could say that, x equals a inverse b. But what happens when this matrix A is not square, right? So when the matrix A is not square, I have a situation like this, where I have basically more equations than unknowns. And the best thing I can do is to solve that equation approximately, as good as I can get, right? So I maybe can't solve it exactly. I can solve it in some sort of minimizing the error that I make, right? It's called a least squares problem. We'll talk about that when we talk about curve fitting in a couple lectures, right? But this is kind of like saying, more equations than unknowns. Hopefully, you have some sense of what to do there, right? Right. The idea is that we're trying to do the best that we can with a least squares solution, right? So, for example, if I say a least squares solution, you should kind of have some sense of what that means. Eigenvalues and eigenvectors, right? So like it will come up that we need to talk about, eigenvalues and eigenvectors, which are basically, if I have a square matrix, they have this special property that when I multiply the matrix by the vector, I get the same vector out just multiplied by a number, right? That number is called the eigenvalue and the vector is called the eigenvector, right? So, you should know about what that means. You're not going to be finding these eigenvectors manually, but we have to understand what the relationship means and why it's important. We should be able to talk about like, what does this notation mean, the norm of a vector, which is like basically the length of a vector in n-dimensional space. We should think about like, something called a hyperplane. Like if I have a situation like this, where I have, this is my coordinate system, and these are my like coefficients, and this is like a constant. What does that look like? Well, it kind of looks like a line or a plane in ND space. Like you've got stuff that's on this side of the plane, some of this side of the plane. So these kinds of ideas, we'll talk about this definitely a lot more, but this is really important when it talks about classification. So a lot of times we're talking about linear classification. It means how can I draw imagine a hyperplane going through this room, a big plane that separates everyone on this side from everyone on that side, right? So this is like the equation of what such a surface would look like. And of course, the more interesting stuff is when, what if things are not separable by just a straight line? Then maybe you have to draw some sort of like weird looking line to decide this decision boundary. That's going to be the interesting part of machine learning. We're going to talk about that. If I wanted to look at, suppose I have, this kind of situation here. So if x is so if x is basically an n by 1 vector, and A is an n by n matrix, right? Then this number here, this is like an n by n matrix here times an n by 1 vector here. Transpose means I flip it on its side. When I multiply all this stuff together, I just get a constant basically, right? So this is just like a number. And so now I have this number. I could think about that's like a function of x, right? I could think about, okay, so what is the gradient of this thing with respect to x, right? That's a linear algebra problem that maybe you have to think about. Turns out the answer is 2ax, but you should be able to convince yourself why that is. It's kind of like the equivalent of taking derivatives in some sense, but with a matrix notation, right? Maybe something that you haven't thought about, but you should be able to think about. You should be able to figure it out from, kind of first principles, right? And then probability, right? So probability, again, you should be familiar with the concepts of, a PDF, probability density function. So you should be able to talk about, like, if I have a PDF, it's this thing that, is a distribution of probability mass that integrates to 1 under here. In general, we're going to talk about PDFs in multiple dimensions, right? So we're going to talk about PDFs over 3-dimensional space or 10-dimensional space or 200-dimensional space. So the idea is that we've got this multi-dimensional PDF. If you took probability, we definitely talked about dimensional PDFs towards the end, right? Joint PDFs. So we're going to talk about joint PDFs a lot in this class because so much of machine learning depends on how variable x is related to variable y, or how one variable is related to 10 features. So that kind of joint probability distribution is something we're going to talk about a lot. You should know what these, e of x means, right? I take x and I integrate it against px dx, right? So this is something that if you took probability with me, you should have drilled into your head by now. We also talk about the variance of x, which is like saying I take x minus its mean squared and integrate over the PDF. The more general version of the variance is like the covariance of x. So if I have two random variables, what does that mean? How do these two things relate to each other? In general, there's something called a covariance matrix, which we'll talk about. So for example, for a Gaussian random variable, we'll talk a lot about Gaussians for sure. You should kind of be able to say, oh, this, I understand what this means. I got the square root of 2 pi. So let's talk about a general Gaussian PDF, right? So something like this. So if you're looking at this and thinking, what is he talking about? Then that's why probability is important for this class, right? So this is like the grown-up version of the Gaussian one-dimensional PDF that we talked about in probability. We talked about the joint Gaussian in probability when I taught it, certainly. This is like the generalization of this to however many dimensions we want, right? So this is just kind of like a, am I ready for this class? If the stuff I talked about in the last few slides seems like, this is something I remember or something I know for sure, then that's great. If any of this is like, I'm not sure about this, then let's see how you feel after the 2 mathematical lectures that are coming up. And that's kind of like the decision point to say, okay, I'm not sure whether I'm able to do all this stuff in this class. So hopefully that helps you give a read for what it is you're going to need to know to be able to succeed here. Okay. Other comments or questions for me? All right. Well, in that case, I think I'm going to knock off. So what I'm going to say is, before you start shuffling, so on Tuesday, remember the Tuesday's a Monday schedule, so no class on Monday, come back here on Tuesday. We'll have another kind of like big picture discussion about, kind of history of data sets and have a discussion about ethics a little bit. And then on Thursday, there's no explicit homework, but I'm going to give you a list of discussion questions early next week where I want you to come to class prepared to actually have a conversation instead of me talking to you all the time. I want to get people talking to me back about things, right? Again, just as a conversation about, how young people think about machine learning. How do you think your parents think about machine learning? Stuff like that. So, all right, thanks a lot, and we will talk to you on Tuesday. Have a good weekend.